In this video, we're going to talk about finding directional derivatives, and we'll define the idea of the gradient. So we've already talked about finding derivatives in two specific directions. We've learned that we can find the derivative with respect to x, so that would be in the direction of the x-axis. And we can also find our partial derivative with respect to y, and that would be in the direction of the y-axis. However, we can also talk about rates of change in any direction that we want. For example, if you take a look at the image I have on the screen, I have a bunch of level curves that are graphed. We could actually find the derivative in the direction of, say, vector u. That would describe how are those z-values changing as we move along a path in the direction of that vector. So how do we find a directional derivative? Well, I have the definition written on the screen. So first of all, we're going to use this notation big D u for directional derivative in the direction of vector u. And if our vector is a unit vector, has a magnitude of 1, then that directional derivative is going to be our partial derivative with respect to x times cosine theta, where theta is that direction angle of our vector, plus our partial derivative with respect to y times sine theta. Again, theta is our direction vector. One other thing to kind of recall here that I have written down in my definition up here, if u is a unit vector, so has a magnitude of 1, with a direction angle theta, we can think of that vector u as having components cosine theta, sine theta. Those would be the components of that vector. All right, so here's my first example. We are going to find the directional derivative of function f in the direction of u for the function x divided by y at the point 1, 1 in the direction of vector u, where I'm defining u to be root 2 over 2i plus root 2 over 2j. So the first thing I'm going to do is find my partial derivatives. And so the derivative of x divided by y with respect to x would just be 1 over y. And then the derivative with respect to y would be a negative x over y squared. So those are my partial derivatives. And then let's see, for vector u, this is actually a unit vector. I know this is a unit vector for several reasons. First of all, I just recognize those numbers, root 2 over 2, from trigonometry. I know that if we have an angle of pi over 4, cosine theta is root 2 over 2, as well as sine theta is root 2 over 2. So this is a unit vector, and it has a direction angle of pi over 4. Again, I just know that from trigonometry. If you didn't recognize those numbers, you could find the magnitude of vector u by taking the square root of the sum of its components squared. And I'm not going to go through that work, but that should simplify down to 1. So that's how you would know it's a unit vector. And then I guess if you needed to find the angle, if you weren't sure what the angle was, you could take the inverse tangent of the y component divided by the x component. Inverse tangent of 1 is pi over 4. I know my direction angle is pi over 4 as well, because both those components are positive. That vector is in quadrant 1 if we start it at the origin. Okay, but regardless, my direction angle is pi over 4. Cosine theta is root 2 over 2. Sine theta is root 2 over 2. And so then my directional derivative, I'm going to take derivative with respect to x times cosine theta plus derivative with respect to y times sine theta. And so that's what I have written down on the screen. 1 over y times root 2 over 2 minus x over y squared times root 2 over 2. And then finally, I can just plug in the point given because I want to know that derivative at the point 1, 1. So I just plugged in 1 for x, 1 for y, did some math, and I ended up getting 0. So this directional derivative is 0. What is that actually telling us in this case? If the derivative is 0 at this angle, then I guess our vector has to be running tangent to our level curves, or now it's helpful to think about these derivatives using some vector notation. And so I'm going to define a vector, and that vector I'm defining is called the gradient. So the gradient for a function of two variables is defined to be a vector such that the x component, the I component, is your partial with respect to x. Your y component or j component would be partial derivative with respect to y. And we call this vector the gradient of our function. And we're going to use that upside down triangle to denote the gradient. I call that operator del, so I might read this as del f. I've seen that symbol called a nabla as well, but I usually call it the del operator. All right, so for example, if we want to find the gradient of the function y ln x plus xy squared at the point 1, 2, again, we're finding a vector, and this vector is giving us partial with respect to x, partial with respect to y. So to start, I am going to have to find both of those partial derivatives. So take the derivative with respect to x for the first term. Let's see, I get a y and then times 1 over x. And then second term, derivative with respect to x is just y squared. Derivative with respect to y, first term, we just get ln x. Second term, bring down the 2, so 2xy. So there's my partial derivatives. And so I can express this gradient as a function. It would be the vector function y over x plus y squared, comma ln x plus 2xy. So there's my gradient vector. Specifically, if I want to know what is this vector at the point 1, 2, I could just plug in 1 for x and 2 for y and then simplify. And so if I did all this arithmetic correctly, my gradient vector simplified down to the vector 6, 4. And again, what those numbers are telling us is the 6 is the rate of change in the x direction, and the 4 is the rate of change in the y direction. So now that I have defined this gradient vector, we can actually define our directional derivative in the direction of the unit vector to be our gradient vector dotted with that unit vector. That's exactly what the formula we had before said. If you think of our gradient as this vector that contains our partial derivatives, we can write our unit vector as cosine theta, sine theta. If we take the dot product of those two vectors, that should give you the formula I had on my first slide. Okay, so now we've got this new, slightly more compact version of our directional derivative. It's our gradient vector dotted with our direction vector. So for example, let's see if we can find both the gradient and the directional derivative of the function sine 2x cosine y from the point pi 0 in the direction of pi over 2 pi. So the first thing I'm going to do is just find my gradient. And so that means I have to find my partial derivatives. So I'm going to start by finding my derivative of the function with respect to x. So let's see, derivative of sine of 2x is cosine 2x times 2. That's the chain rule. And then that cosine y stays there. And then derivative with respect to y, the sine 2x stays there, and then times negative sine of y. So there's my gradient vector. I'll just simplify that by putting the 2 in front of the cosine 2x cosine y, and then I just put the negative in front of the y component. Just looks a little bit nicer that way. The point that we're interested in is this point pi 0, and so I can actually find my gradient at the point pi 0 by plugging pi in for x and putting 0 in for y. And so I'm going to go ahead and do that arithmetic, and this simplified all the way down to the vector 2, 0. Okay, so partial derivative with respect to x is 2, with y is 0. And then, finally, I want to figure out, okay, what is my direction vector? So in what direction are we finding our derivative? And so I'm going to call that vector PQ. So we're starting at point P, and we're going in the direction of point Q. So vector PQ, if I take terminal minus initial point, I get the vector negative pi over 2 pi. So that's the direction we're moving in. If I want to use this dot product definition, the fact that my directional derivative is my gradient dotted with my direction vector, I do have to change PQ into a unit vector. And so to do that, I'm going to find the magnitude of vector PQ. So I took my x component squared plus my y component squared, and then I'll just take the square root of that. Let's see, we could do a little bit of simplification here. Pi squared over 4 plus pi squared is 5 pi squared over 4. And then I can take the square root of both the pi and the 4. The 5 will have to stay under the square root, and so the magnitude of that vector is root 5 and then pi over 2. So that's the magnitude of my vector. So unit vector in the direction of PQ, I'm going to take each of my components and divide them by that magnitude. So negative pi over 2 divided by root 5 pi over 2. That just turns into negative 1 over root 5. And then the y component, I take pi, I divide it by that magnitude. Let's see, copy dot flip. I end up with 2 over root 5. So there is a unit vector in the direction of PQ. So finally then, if I want to find my directional derivative, I can take my gradient and I can dot that with my unit vector, find the dot product. And so in this case, I end up getting 2 times negative 1 over root 5 plus 0 times 2 over root 5. That's negative 2 over root 5. And so that is my answer. And what that is telling me is that the z values, the outputs, are decreasing at that rate if I move in the direction of vector PQ. All right, so a little bit more information or some properties about our gradient vector. If our gradient vector equals 0, so again, the gradient is a vector. So I'm saying when I say equals 0, I mean both components equal 0. So if our gradient vector equals 0, then our directional derivative is 0 in every single direction. So regardless of what direction you move in, the derivative is going to be 0. Okay, property number 2 says the direction of maximum increase of f is given by our gradient vector. Okay, so the gradient vector gives us the direction of maximum increase of f. And the maximum value of that directional derivative is the magnitude of our gradient. The minimum increase is in the opposite direction of our gradient vector, so negative gradient vector. And then the minimum value of our directional derivative would be the negative magnitude of that gradient. So let me explain those second two properties in a little bit more detail. So we learned our gradient vector contains our partial derivatives as components. So f sub x is our x component, f sub y is our y component. If we find our directional derivative in the direction of that gradient, well, I'd have to change my direction vector into a unit vector. So I'd have to divide by its magnitude. So what I have on the screen, vector u, is a unit vector in the direction of our gradient. So then the derivative in the direction of that gradient would be del f dotted with u. So I'm going to write that out, del f dotted with u. So f sub x times f sub x divided by the magnitude plus f sub y times f sub y divided by the magnitude. And we can simplify this down a little bit. So we end up getting f sub x squared plus f sub y squared over my square root of f sub x squared plus f sub y squared. If we rationalize the denominator, if we multiply by that square root on the denominator, we end up getting something that we can simplify. We have these common factors of f sub x squared plus f sub y squared. And so what just happened here is the derivative in the direction of our gradient is the magnitude of that gradient. That's what I've just shown here kind of quickly with all this work here. But I wanted to show you where that property 2 kind of, at least part of that property comes from. Okay, so again, the direction of maximum increase, so the maximum value of your derivative is going to be in the direction of that gradient vector, and it's going to have a magnitude equal to the magnitude of that gradient vector. All right, so let's see how this works by doing a specific example. Let's consider the function f of x equals y squared plus x. So we're going to do 4 different things. We're going to start with part A. Let's focus on that. Find and graph a level curve to the function at the point 4, 1. So first of all, which level curve are we talking about? If we're at the point 4, 1, x is 4, y is 1. If I plug those numbers into my function, I get an output or a z value as 5. So basically they're asking me to find the level curve for c equals 5, or I guess you could say z equals 5. So draw the level curve that gives heights of 5. And so what I did is I just plugged 5 into my f of xy. So plugged 5 into my f of xy. So my level curve is going to be 5 equals y squared plus x, which is the same thing as x equals 5 minus y squared. And so I'm going to sketch that graph. So this would be, let's see, it's a negative y squared, so it's a sideways parabola. And then it starts 5 units, I guess, to the right of the origin. And I plotted a couple points. If you aren't sure what that looks like, you could plot some points. For example, if you plug 0 in, you just get x equal 5. So there's the point 5 and 0. And then if you were to plug, say, y equals 1 in, you would get x equal 5 minus 1 or 4. And the same would be true if you plug in y equals negative 1. And so there's my point 4, 1. Should also go through the point for negative 1. And so in blue is my level curve, and it does go through the point 4, 1 as they asked in the directions. All right, part B, find and graph the gradient at the point 4, 1. So find and graph my gradient vector at the point 4, 1. So to find my gradient vector, again, I have to find my partial derivative with respect to x and my partial derivative with respect to y. So for the function given, derivative with respect to x is 1, and the derivative with respect to y would be 2y. So my gradient is 1, 2y. And then at the point 4, 1, if I plug in x equal 4, there's no x's. I plug in y equal 1, I get the vector 1, 2. So there's my gradient vector, 1, 2. And then I'm going to graph that vector at the point 4, 1. So I just went over 1, up 2, and so there's my gradient vector. So that was part B. And one thing I want to kind of make note of while I have this on the screen is notice that my gradient vector appears to be normal or perpendicular to my level curve. My drawing is a little sloppy, so it may not look perfect, but it should look normal to that level curve. It's not a coincidence. The gradient is always normal to level curves. Okay, so our gradient vector will always be normal to level curves. What is the maximum value of the directional derivative at that point for 1? Well, on our previous slide, we actually just learned that the largest directional derivative, the largest rate of change, is going to happen in the direction of that gradient, and it will have a magnitude that is equal to the magnitude of my gradient vector. So without actually having to find the directional derivative, I know that the maximum value is going to be the magnitude of that gradient vector, which is the square root of 1 squared plus 2 squared, or root 5. So maximum value of my derivative occurs in the direction of that gradient vector and has a magnitude of root 5. And one way to kind of think about why this happens is, again, if you've ever used like a topographical map, like a map and you're out hiking and you're looking at the little topo lines or the level curves or the contours, if you walk in a direction that's perpendicular to those contours or those level curves, you're going to be going very steeply uphill. That's the steepest direction you can walk. Whereas if you walk parallel to those contours on your topo map, then you're not going to be going uphill. And so that's kind of the concept here. Finally, part B says find and graph a tangent vector to this level curve. So our tangent vector is going to be orthogonal to our normal vector, and the gradient is always normal to the level curve. So that means, since my gradient is 1, 2, a vector that is orthogonal to the vector 1, 2, or perpendicular, would have components that are flipped, and one of them has to be the opposite sign. So either the vector 2, -1 or the vector -2, 1 would be appropriate. Both of those vectors are going to be tangent to this level curve. It just says find a tangent vector. It doesn't specify which one. So I just randomly chose to draw the vector 2, -1 on that graph. So a couple more comments about our gradient. So I have on the screen an example of level curves. This is actually a weather map, and these are temperatures. And so we could talk about the temperature gradient when we look at this map. Our temperature gradient vectors are always going to be normal to our level curves. So for example, at any place, for example, if I look, I don't know, right here, at that particular location, looks like, what is that, Tennessee, southern Tennessee. If I want to draw my gradient vector, it's going to be normal to my level curve, and it's going to point towards the higher values of z, or in this case, temperature. So I know my temperature gradient would look something like that. Or, for example, I don't know, if we move into Colorado, let's say I look at this point right here, my gradient vector would be normal. Oop, there we go. And it would point in the direction of the higher temperatures. The gradient is going to be larger when our level curves are closer together. So where on this map will we have the largest temperature gradient? I would say in this region right here, it looks like kind of in the Arizona area. The contours are closest together, and so the gradient vector would be largest, the rate of change is largest in that region. All right, so just a couple of details about that gradient to help us think about it in kind of more of a real-life situation. Now, we can extend all of these ideas to functions of more than 2 variables. So far, I've only done my examples with functions of 2 variables, but we could find a gradient for a function of 3 variables or 4 variables, just extending that idea. So the gradient vector for a function with 3 variables is going to have 3 components: derivative with respect to x, derivative with respect to y, derivative with respect to z. And we can also find directional derivatives by taking our gradient vector dotted with our directional vector. It's just if we have a function of 3 variables, our direction vector is going to be a 3-dimensional vector. It's going to have 3 components as well. So same ideas, we can extend them to functions of more variables. So for example, if I'm going to find my gradient vector for the function x e to the yz, I'm going to find my derivative with respect to x. That's just e to the yz. My derivative with respect to y would be x e to the yz, and then with the chain rule, I have to multiply by the derivative of yz. That's just z. So x e to the yz times z. And then similar reasoning, my derivative with respect to z is x e to the yz, and then the derivative of yz with respect to z is just y. So chain ruled that one as well. So my gradient vector would be e to the yz, and then I'll just rewrite the next term as an xz e to the yz, and then last component xy e to the yz. So that's part A. There's my gradient vector. If I want to find the direction of maximum directional derivative at the point of 2, 0, -4. Okay, so part B is saying in what direction would you have to go from that point given to get the largest value of your directional derivative. And we learned earlier that that's going to happen in the direction of the gradient. So to answer part B, I just have to find the gradient, the value of that gradient vector, at the point 2, 0, negative 4. So I'm just going to plug those numbers into my answer for part A, into my gradient. So let's see, e to the 0 is 1, and then I get a negative 8, e to the 0, that's negative 8, and then last component is just 0. So in the direction of the vector 1, negative 8, 0, we will have the maximum value of our directional derivative. And if we actually want to know what is that maximum value, we just have to find the magnitude of our gradient. So magnitude of our gradient vector would be the square root of 1 squared plus negative 8 squared plus 0 squared. I got square root of 65. So that would be the maximum value of this directional derivative. All right, that was my last example. Please let me know if anything is unclear.